Alright.
Was yesterday's session the same as this?
No, actually. So yesterday was vector calculus. It was recorded. Don't fret about it. And today is going to be about complex analysis. Alright? So we're kind of picking off from where we left off yesterday. Okay? Alright. So, welcome to part 2 of the math... Oh, no. Let's try not to make too much of a mess. Right, there we go. Part 2 of Math2069, Math2A. We're going to be covering complex analysis today. Alright, so we have about 2 hours for this and 130 slides to get through, so we're going to be going a little bit quickly. If you have any questions, please feel free to ask them whenever. If you're in the room, just like either put your hand up or whatever. If you are online, just chuck it into the chat, and let's get moving. So, complex numbers come first as our intro to complex analysis. Quite frankly, we have our Cartesian form and our Euler form, and we use them in pretty standard ways. Moving forwards, concept of magnitude and concept of principal argument. They'll come back later. We should know what we're doing. All right, so more things to consider. We have certain inequalities that we want to be obeying with our complex numbers. General vector stuff, pretty much. We have triangular inequality. So if we have A, B, C, we know that A plus B must be at least C, okay, in terms of magnitudes. Similarly, for the circle inequality, the way that I like to think of this is having one point on a circle. It can point in any direction, and from there, we draw another circle. And the minimum value is given by just the difference between the lengths of those two circles, okay? It's a little bit intuitive in the sense that there's a relative phase between this complex number and this complex number. And using that relative phase, there is a minimum given by the absolute value of the difference of the absolute values. Following? Fantastic. All right, moving forwards. Topology and sets, just a little bit of terminology. We probably also covered this in the vector calculus area just a little bit, but we'll get moving anyways. A set is open if every element of the set is an interior point. Interior point just means that here's a boundary, here's a point inside of it. I can zoom in however much I need and draw a circle about that point that is entirely inside of my set, okay? So that's all an interior point is. There is some ball such that the entirety of it is inside of it. Okay, next up we have closed, which can be one of two things, both are equivalent. The first one is that it is, it contains all of its boundary points, or its complement is open. So probably just the easiest way to think of this is I can trace around the edge of my entire thing and form a boundary. All those points are included, okay? Perfect. Now we have bounded, just means we can draw some manner of circle around our entire set. That's really all it is. There's some circle, some kind of ball centered about 0 that is big enough. Of course, with a finite radius. All right, next up we have the regions. Regions are basically just open sets with some quantity of their boundary points. So if I were to draw this kind of shape, including this point, then it is not a region because this is not a boundary point of the open set included, right? All right, let's get moving. Quick example, we have 4 different regions. Sorry, we don't know if there are regions yet, just yet. So first up, we have magnitude of z is less than 1, so that is actually going to be a dotted line around a circle, including the middle, so this will just be 1. Number 2, we have the real numbers between 0 and up to 1, not including 1, so if we draw our Argand diagram, that'll be including 0, but not including 1, so that's 1, and everything in between, okay? Next up, we have number 3, which is just the single point 1 plus I right here, and number 4, which will be an annulus. Alright. Mind you, it is an open annulus. The boundaries are not included. So we're just going to run through, okay, is it open, closed, bounded, connected, simply connected, or a region? Okay, all that jazz. So open, closed, number 1, clearly open, no boundaries included. So say open. Is it bounded? I mean, it is a circle, so that is pretty much given to us. Connected, yeah, we can draw a line or some manner of arc between any 2 points inside of it. Simply connected just means if we draw some manner of polygon inside of it, then the interior of that polygon is also included, okay? Just a little extra terminology. And regions, we can clearly see that all of these are regions. Number 3 is a little bit of a special case, but I'll get to that in just a moment. We know they're regions because we can clearly identify an open set. For 4, it is this annulus section. And so all of them will be regions. In the case of number 3, we actually want to be really careful because we could call our open set that we're dealing with the empty set, okay? In which case, there is 1 point on its boundary. Any 1 point. Okay, so this could be considered a boundary point. And this kind of just stems from, okay, let's look at the complement of it. It would be everything except for this point, which is an open thing, meaning that this one specific point is on a boundary. Okay, so little things like that, we won't fuss over it too much. Next up, let's talk about just the following ones. Open, closed, neither. It's got a closed side and an open side, so neither. Number 3 has to be a closed set because it is all of its boundary points, quite frankly. And then number 4 is going to be an open set. All right, we can continue through and just determine the rest of the values as set up here. But it should be rather intuitive at this point. Okay? Going well? All right, fantastic. Let's keep on moving. So we got complex functions. Complex functions are just really a mapping of complex numbers to typically other complex numbers. And so going from there, we have to talk about mappings. Here we have a specific type of mapping where we really only need to deal with 3 different types of operations. First operation is a reciprocal. The second operation is x shift. The third operation is a y shift. Okay? And I'll just explain how we break this down. Okay? Mind you, this little condition is sometimes imposed just to say that we're not dealing with a constant. Okay? So I will now explain. When we try to break this down, okay, we can obviously divide by cz plus d to factor out this little z on the top. So that gives us some manner of constant out the front, alpha, plus beta on cz plus d. Okay, I might just go ahead and say multiplication is another operation we use, but it is fairly intuitive. So the way that I like to deal with these is just consider it a little bit graphically, just to give some intuition to it, right? So if I have some set of points z, what do I need to do first? I just need to multiply it by c. Okay, what does cz look like? That gives me w. Now I need to right shift it, or shift it however by d. D is a complex number. So I do w plus d, gives me some new complex number. Let's call it u. And then I'm taking the reciprocal of that. So I'm going 1 over u. Let's call it v. And then beta times v gives me, let's use x. And then I use x plus alpha finally to give me y, which would be my resulting transformation. This kind of built-up intuition can help you with just really throwing yourself in the deep end, double-checking your answer. However, a more appropriate method would be to break it down into, okay, we're going from some function of x plus iy is going into u plus iv, okay? And so the best way to do this is to go ahead and typically we have z goes into what we had here, which was az plus b on cz plus d. We want to rearrange this such that if we say f of z equals w, well, what does w look like in terms of z, okay? And then we can go ahead and define u and v in terms of x and y, okay? From there, we can impose the conditions on x and y, which define our set on z, and then just work backwards to find what it looks like, okay? So we're just going to run through a similar example to that right now. So, as we said, we have a mapping. Whoop. The mapping is given by 1 over z plus I, okay? So, two ways to look at this. We could go ahead and shift it up 1, because z plus 1, and then take the reciprocal, or we can just break it down as we are doing right now. So, if w equals 1 over z plus I, then we have z equals 1 minus iw on w, okay? If we decompose this into x plus iy and u plus iv, we obtain our conditions, okay? Now, given the restriction on z, we can now substitute for u and v, okay? And so this tells us what is our mapping, our image, going to look like. All right. So doing so, we just plug it back in to the condition provided. So 3 times x, which is going to be u on u squared plus v squared, plus y, which is going to be minus u squared minus v squared minus v all over u squared plus v squared, is equal to 1. And we can just work this through. It turns into a circle. Let's look at the shifting, and bam, we end up getting it, okay? And it turns out to be a circle. All right, any questions so far? All good? All right, sounds all good. So, next up, we have a quick practice question. So there's a little trick in here, and I think that little trick is right here. Basically, iz minus 2, the magnitude of this is equal to 2. So first things first, we have to find out where is this kind of a circle centered, okay? If we go ahead and look at iz minus 2, we have to go ahead and find the center. Center will be given when the magnitude is 0, and so we say, okay, center is given by iz minus 2 equals 0. Work it out. Z equals minus 2i. Yeah. Alright. Now, given that we have a center, we have the radius, and we can just go ahead and perform the mapping. So, mapping of 1 on z, we'll do it a little graphically this time, just for a bit of intuition. We know that this is a circle with radius 2 about minus 2. Okay, minus 2i. Circle looks like this. If we perform 1 over z on this, okay, a little bit of intuition about these 1 over z transforms is that if we have a circle that touches the center, the origin, then 1 over z will bring that to a straight line, simply because our origin maps out to infinity, okay? Little bit of intuition there, but we move forwards. 1 over z over here should bring us to 1 on 4 I up here, and then we get our straight line. Yeah. So little bits of intuition can give us a lot of information. This is a bit of a graphical one. Feel free to do it at your own leisure. We're going to keep on pushing forwards. All right?
So is the image just a straight line?
Yes, the image for this one is just the straight line given by y equals 1 and 4. All right? I believe. It should be. Anyways, one more example. It's just going to be using our inequalities, okay? Just so we, once again, gain a little bit of intuition. When we're given that the magnitude of z is going to be greater than or equal to 2, and we need to prove something about z being on the denominator, easiest thing to do is look at which direction we need to prove from. We're proving that our value is smaller, therefore the denominator must be bigger, okay? Because absolute values break down into absolute value of 1 over absolute value of z to the 4 plus 1, which we only really need to consider the denominator. Okay? And moving from here, we have to think about where does this go and what we know about it. What we know is that there is a worst case scenario and a best case scenario. In the worst case scenario, this is going to be its biggest form. Okay? And so we look to maximize it. Maximizing means we minimize the denominator. Minimizing denominator, oh, we have the circle inequality applied right here. And so we end up with 15, since the magnitude of z was going to be at least 2. All right? Fantastic. Now we're just going to jump straight into limits and differentiability. That was just a little intro to complex numbers and inequalities, just so we can get moving with later parts of the course. So, limits and differentiability. We understand limits, epsilon delta definition. As I get closer to this point, in whatever graph or mapping that I'm using, then I expect that when I transfer this into my image, I also get closer to wherever that point is, right? However it works, okay? So it's just a manner of convergence as we go towards that point. We love limits. So, biggest thing to take away from this is that the limit does not exist if we can take two different paths to it and we get two different values, right? Because, well, ideally, what I have is a continuous function. However, some functions are not continuous, quite frankly. And it gets a little interesting with complex numbers specifically, because now we're not just talking about, okay, from the left, from the right. We're looking at, okay, every direction, which gets a little interesting. So, let's jump into a question. Let's prove that the limit of the imaginary component of z over z as z goes to 0 does not exist. Well, easiest way to do this is to convert it into our polar forms, and that way we can just let r go to 0, okay? And ideally, our result will be independent of theta, our angle, right? Because the angle, all it's telling us is the angle at which we approach the point 0, right? And so we find that our limit value is dependent on theta. Therefore, no limit exists because it's obtaining different values from different paths. All right? Fantastic. Let's keep on moving. So, a couple of properties of limits. It is somewhat intuitive. We just want to look at particularly this. Our real and imaginary components are like two separate parts of a function. Therefore, when we deal with the limit of f, the real approaches the real part, the imaginary approaches the imaginary part. Alright, moving into continuity. It is continuous at every point A, okay? That's just when you are continuous at A. It shows that the limit is actually equal to the functional point, okay? And should be defined. So, where it is defined. Fantastic. Let's keep on moving. So, here we have an example. We're just proving that the imaginary component of z is continuous as a function, okay, for all the complex numbers. And the easiest way to think about this, once again, we're using limits. If I have some path I'm taking, my imaginary component of z, where is it? How does it change? And how does that change with my distance to that said point, okay? And we'll actually find that the worst case scenario is when my imaginary component is being approached just from the imaginary axis, okay? And so we talk about epsilon delta, and we just choose delta to be epsilon. That should be epsilon in here. And doing so, we can actually just prove that given that magnitude of fz minus fz naught is equal to the difference in the imaginary components, by the triangle inequality, it is going to be less than the actual magnitude between the two components, which is our delta, which can be epsilon. Okay? Fantastic. And so it is continuous. Any questions so far? All good? Ish? All right. So let's keep on moving. So differentiability. Differentiability is just saying that, okay, when the limit, as I look at the rate of change, occurs, if it actually converges to a certain specific value, then it exists, okay? And so the easiest way to think of this, it actually gets really interesting in complex analysis as well. Easiest way I find to think of this is, okay, some curve, 2 points, and we're just measuring gradient between them. And as those 2 points get infinitely close, we get a limit, that is our derivative. Fantastic. Ends up being tangential. However, in complex analysis, this actually has a much more interesting implication. It actually implies that if I'm looking towards some point A, okay, and I look towards it from any of these positions, right, then when I divide the difference in my function from whatever point I am to that point by my actual vector between the two, I get a constant value if it's differentiable, okay? And that's really interesting because it means that if I have a complex function that is differentiable, if I move it up by some tiny amount, then the difference between, let's call this z0, that tells me that f of z0 plus epsilon equals f of z0 plus, let's say, the derivative. Let's let f dash z0 equal a. It tells me, okay, equals a epsilon. And this is really interesting in complex numbers because epsilon is a complex number. Epsilon can be in whatever direction. And so if I take this to be really small, then it also means that z0 plus I epsilon equals f z0 plus I a epsilon. And so really, if note A is a complex number in complex analysis, it tells me that, okay, if I have a point and I move away from it this way, or I move away from it this way, then in the mapping of that, if the red one moves away this way and it is differentiable, then the black one will move away that way, which is just a really interesting result. Anyways, this gives us our Cauchy-Riemann equations, which, if you look back on vector calculus that we did yesterday, it actually turns out resembling curl-free functions. Okay, curl-free just means that if it is your nabla cross your function gives you f2 minus f1 whatever. right? It actually ends up being equal to 0 in this case, okay? For all complex differentiable functions, okay? And that has very nice implications. These will be our best friends, and they are the two primary conditions for a complex function to be differentiable. And it actually tells us where they're going to be differentiable. So we have a couple of examples ascertaining to that, all right? So f1 z times magnitude of z squared. We go ahead, define it in terms of x and y. We get a real part, imaginary part, u and v. If we differ with respect to x, u dash x should be equal to v dash y. So these two should be equal. However, this only occurs when x and y are equal or opposite magnitude. And then when we say that vx and uy would be negative, then it's only really equal at one of them being 0. Okay? So just using these conditions, we can actually ascertain that it only works when both of them are 0, and therefore only at the origin. Moving forwards, f2, we have x cubed plus y cubed as our function value. It's already given in x and y, so now that just gives us u and v immediately. We can work that through, and we get a somewhat similar result. Okay, it is only differentiable when x is equal to plus minus y. All right, and so that would just be along these diagonals of the complex plane. All right, I'll actually do that in a different color. All right, nice. And then finally, we have the function of z is equal to the magnitude of x plus I times the magnitude of y. And we can kind of treat this case by case, saying that in certain regions this will work, this won't work. And yeah, the way we define the derivative of these things, usually we would go ahead and make it a piecewise function, where we say, okay, it's going to be x over here and minus x over here. But instead, by taking the derivative, we can actually just divide it by its magnitude, and that gives us the direction it's in, right? Which will be either 1 or minus 1. And therefore, we just chuck in our Cauchy-Riemann equations, and it tells us that it's differentiable when x on y is greater than 0. Okay? Fantastic. Analytic functions next. Oh, we have a question online. The slides, I believe, do not have a present place for download. It may be organized at a later date. Yeah. Okay, analytic functions. We have a definition, okay? Analytic just means it's differentiable on a open set containing some point, okay? So typically, we use analytic in a subset manner. So we say this is analytic on this subset because it is analytic at each point in there, okay? Which just means within some open set. Fantastic. Next up, some more info. We're just info dumping at this point. Harmonic functions, really interesting result. We just get the partial diff of u with respect to x squared, and the partial diff of u with respect to y squared is equal to 0. Okay? And this is actually how we can determine our harmonic conjugates. Okay, so if we have u, we can find v, we can find u. And it's all just using our harmonic function as well as the Cauchy-Riemann equations. Okay? So here we have an example. Given that u is equal to sine x sine y is a harmonic function, show that it is harmonic and find its harmonic conjugate. Okay? So harmonic, we go ahead, perform the double diff, we get value 1. We perform the other double diff, we get the negative of it, sum must be 0. Fantastic. It is harmonic. Now we find harmonic conjugate, so we determine du on dx, that becomes dv on dy, right? And so this will actually give us the function in terms of y. Sorry, this will give us vy, which when we integrate with respect to y will be equal to v plus some constant, which will be a constant with respect to x. Because you can imagine if I partial diff v with respect to y, I lose all of my x information, okay? Purely x information. But at the same time, I can go ahead and do the same thing to determine vx, okay? And so, if I actually go ahead and I use this, and I go ahead and I go dv on dx, then this should give me some information ascertaining to this extra function in terms of x, because I have that knowledge hidden inside of this Cauchy-Riemann equation, okay? And that's actually just exactly what we do here. So first up, we have v in terms of y, which gives us a constant in terms of x, because partial differentiation, we treat something that we're not directly dealing with as a constant, okay? So to find cx, we go ahead and we say that, okay, this value differentiated with respect to x, just partially differentiated, this one right here, will give us minus uy, okay? And uy is over here. So it gives us minus uy, therefore it tells us that c dash x doesn't exist, okay? C dash x is going to be 0. And so since it is 0, it is some constant value, and mind you, all harmonic conjugates, you can use u to find v, and then you can add any constants you like, okay? Constants that are not in terms of x and y, just imaginary numbers, okay? And so we find a, emphasis on the word a right here, a harmonic conjugate. And so we can just set it to be 0. So that gives us v. Fantastic. All right, any questions so far? We all good? All right. Another question. Basically, we're just showing that v is a harmonic function and finding some value u such that we get an analytic function for all x and y that are elements of real numbers which make up our complex plane, okay? So really, we're just doing the exact same thing again to find an analytic function, okay? So running through the motions, we get vx equals minus uy and ux equals vy as above. It's pretty quick to determine them using our cos, sine, and rest of our differentiation rules. And once again, we apply them until we get a constant in terms of x, differentiate to determine what that constant should be, right? So over here, we actually end up getting that the constant should be of the form 2x cubed plus some constant, some complex constant. And so we can determine a analytic function where this is 0, so we tack on the plus 2x cubed. All right, so this gives us u, and therefore our full function is analytic. All right, just because the Cauchy-Riemann equations are satisfied everywhere. Fantastic. So next up, we have a bit on the exponential function, and it'll be diving a little bit into Taylor series, but first, just some information. So the exponential function is given by the result of the series, summation from n is 0 up to infinity of z to the n over n factorial, and this holds for all complex numbers. So typically we've seen this with real, now moving into complex analysis, we love it. And likewise, we can actually break this exponential value of z down into real and imaginary. Z goes into real and imaginary, which gives us a magnitude and a phase. And therefore, it actually can tell us a lot more about whatever that complex number is. Moving forwards, the composition of complex functions, composition of exponential functions, we have Cauchy and Shine with their respective Taylor series. We have a couple properties ascertaining to them just with our compound sine rule, compound cos rule, and derivatives. They're pretty similar just in terms of everything except for this little fancy plus, which would typically be a minus when we do cos compound angle rule. And then derivatives, they just flip between the two. Okay? And we'll just keep on moving. Just because this is a bit of an info dump, just so that you guys can record down all your stuff if you need. Alright. So, I guess now we move on to our trigonometric versions, and you'll actually just find that cos z is the same as cosh, just with an I attached to the z. Okay? And that gives us a little bit of a bonus thing a little later. Same thing with sine, however, there is now an I on the denominator as well. Okay? Pretty stock standards, so we'll keep on moving. Alright? Now we hit the fancy part. We're going to start trying to find an inverse for our exponential function. And so this brings forth the principal branch of the logarithm. So, logarithm, why is it important to have a principal branch? It's so that I can get one specific value rather than my multi-valued log function. And to do this, I'm just restricting whatever arguments I'm giving out. Okay? And so we'll actually go ahead and try and use this, the principal valued logarithm, to solve cosh of z is equal to minus 2. Okay? So, once again, cosh of z is just going to be equal to e to the z plus e to the minus z on 2. Okay? And we learned before that we can break this down into x plus iy, but as of right now, this is what we'll deal with. And it actually really, most of them of this form will always break into a manner of quadratic. Okay? Because we just treat e to the z as our variable, and we solve for it as such. And that would give us two values right here. However, in some instances, you might find that you are left with a imaginary complex number in this square root. You shouldn't need to worry too much about this, just because the plus minus does account for both roots of that. Okay? So, moving forwards, we go ahead and yeah, now we have e to the z as that. Now we can use our logarithm. So, the logarithm, just remember, log of z is equal to log of r e to the I theta, which is just going to be equal to log r plus I theta, in a sense. Okay? So this is the way that we want to break it down. And so the way that we express this in terms of z again is log of the magnitude of z plus I times principal argument of z. Alright? As we had above. Right now, it's not really asking us for the principal value, we're just doing the logarithm itself. So first things first, we get magnitude of z in here right now, and then argument of z in there right now, in the imaginary component. Okay? And this gives us z as required. Just note, we have a minus 1 just because, we have an I pi just because the minus 2 plus minus root 3 is always negative. So we flip that around inside this normal logarithm. so we can remove the absolute value signs. Anyways, now we have branch cuts. Okay, so branch cuts are really just, okay, I do want a single valued function, not a multi-valued logarithm, but let's keep the angle within some certain bounds, because all it is restricting this imaginary component, okay? Simply because our argument is a multi-valued function, okay? So, doing so, we define our branch cuts. So, if we define some value theta for log theta of z, then we're actually taking our value of the argument from theta to theta plus 2 pi. All right? Nothing too special with it, but we always understand that the derivative with respect to z is always going to be 1 on z, okay? Because it's just about rates of change. Rates of change are typical. Note that this is differentiable in analytic everywhere except for the branch cut, because on the branch cut, it is as though we have a jump, okay? So typically, when we run around in a circle from minus pi to pi, just in this tiny instance, there is a 2 pi jump, okay? And that's a discontinuity. And when we stretch that into our logarithm function, that goes ahead, puts a minus pi to pi here. You have a function that moves down, probably hits it, and then reappears up the top. And that there is your discontinuity. Okay? All right. As for formula sheets for the final exam, I'm not too sure about the specifics on that. However, a fair bit of your stuff should be just derivable just from how we define our trigonometric functions. Just a question from the chat. All right, moving forwards. Choosing branch cut, here we have an example question. We're going to find whatever branch cut we can use such that the imaginary component is valued at 7 pi I when we take the logarithm of z equals minus 1. And really, all that means is when we draw the Argand diagram, I'm taking minus 1, which will just be over here. And when I measure that, I want to go around 4 times. Right? On the 4th time, I hit that. Okay? Because the first 3 build up 6 pi, 4th one gives me the 7 pi I. Okay? And so, how do I define this? Well, I want to be very sure that I'm not excluding 7 pi I. And so, one way to do this is just to have 7 pi I being directly opposite from the branch cut. And so, we could take the branch cut from 6 pi. Okay? So, you'll actually see in the working out just over here that by taking the branch cut at 6 pi, it makes sure that our logarithm is actually defined at 7 pi I. Sorry, defined at z equals minus 1 for it to return a value of 7 pi I. All right? Fantastic. Another example, where is this function differentiable? Okay, so earlier we saw that, okay, our logarithm is only not differentiable when dealing directly with this line, okay, because we have a jump discontinuity. And so the way that we deal with this is we say, okay, for this function, where is this line? It's another mapping, funnily enough. It's just 3iz minus 4. We want to find when is it negative, okay, just a negative real number. And so we proceed with our working. Function is differentiable everywhere except for minus pi to 0. And so we set it up to equal to that. We determine z is equal to 4 on 3i. Or other words, we have minus 4i on 3 times k. K is some real number. Fantastic. So it's just about finding where that differentiable zone is, non-differentiable zone is, and then taking everything else. All right? Sounds fantastic. We have another example. This time it's using sine instead of shine or cosh. Cosh, yeah. And you'll actually find, wow, immediately put it into a quadratic, because that is the nicest way to get rid of one of our groups of e to the iz, and then just solve the rest. It is pretty systematic, the way that we solve these. Probably just the biggest thing to note is here we have all complex numbers, so we want to include the 2 pi I, so we end up including it in the arg because it is lowercase, and we immediately push that into over here. Yeah, all right, and then now we can start talking about complex powers. So complex powers, usually perfectly fine. We just take to the nth power, but now we're taking reciprocal powers. That's where it actually comes in, complex roots. So given that any complex number can be written as z equals logarithm of e to the z, or rather z is equal to e to the log z. This was a little silly. But yeah, since we can write it in this manner of form as e to the log z, then we have z to the alpha equals e to the log z alpha, which is e to the log z times alpha, right, since this bit is our z, and therefore we can just really determine what the logarithm value is going to look like. So if I say, okay, log of z to the alpha, it just gets rid of this e, brings down everything on top, which will just be alpha times log z, which we understand just from log rules. But it actually gives us a nice result, especially when we want to find a specific value for it. So the main issue here when taking roots is when I draw a unit circle on the complex plane, if I have a complex number defined by 1 plus I all over root 2, then when I square root this, there's one of two ways I can go. I can either half it going towards the origin, or I can half it going towards the negative side. Okay? In any case, my argument is halved. In one instance, my argument is measured in the clockwise direction. In the other instance, it's measured from the anti-clockwise direction. Okay? And so this principal value thing is going to be a restriction on our argument. Okay? Just applying our principal value function of log. So the definition carries over to influence broader areas, is all. Okay? And so we're saying that when we square root a complex number, the domain is going to be restricted to the first and fourth quadrants. Okay? Because in this instance, we're taking principal argument of z divided by 2. Okay? So it's purely talking about principal arguments now. This is how we define the principal branches of complex roots. Okay? And so this comes up as a way that we, once again, avoid multi-valued functions. Okay? All right. Now I have a bit of a question bash. Okay? And we'll probably just try and bash out all of these questions within the next 5 to 10 minutes. So, first things first. We have from the 2018 final exam question 3, part 3, find the value of I to the power of 2 minus I. The principal value of it in Cartesian form, and then which of the following values is the principal value within your multi-valued. So that's our first question we're going to be bashing out. Feel free to pause if you're online so that you can attempt this yourself and then run through it. In the meantime, we'll just go ahead and look at the other questions as well, because it will be a little bit intuitive, just the systematic process of breaking it into the log and then working out the exponential. Next question we have is from the 2021 final exam, question 2, part 2. Express log I minus root 3i in Cartesian form, and then hence determine the principal log of it in Cartesian form again. So multi-valued to single-valued. Once again, we go ahead, logarithm of a complex number, logarithm of the magnitude plus I times argument. Okay, argument is plus 2k I pi over here, and we just remove it for the principal one. Okay, and so we just get first bit. Fantastic. And then another question is going to be from the 2015 final exam, question 4, part 1. Find the exact value of the principal value. Sorry, I'll try and fix this one up. This one's a little bizarre, sorry. We might leave that one for now. My apologies for the formatting on that one. I believe, never mind. So we have 2015 final exam, question 4, part 3. Principal value of the square root of z squared plus z to the minus 2. Where is it analytic? So let's go ahead and look at this. So analytic, we recall, that's just where is it differentiable on an open interval. Open set. So principal value, once again, we take let's just go up and call it. We get 1 over n being the exponent attached to the magnitude, and then we go ahead and then we affect the argument as such. So in this intuitive sense, let's go ahead and have a crack at it. So the principal value of root z squared plus z to the minus 2 is going to be equal to the magnitude of z squared plus z to the minus 2 taken to the half times e to the I principal argument divided by 2. Okay, and so that'll just be arg z squared plus z to the minus 2 on 2. So now we just have two things we need to find. Okay, and so let's go ahead and determine where it is analytic. Okay, so we need to take a derivative. First things first. So to tell when a principal value function is analytic, we need to be thinking about where are the endpoints at which there are discontinuities. Okay, and for us, that will really only be within some manner of region on the complex plane. So if I'm taking an nth power, my principal value lies in here, lies in this box, where I take some angle being pi on 2n going in two directions. And then I can just work from that, okay? So let's go ahead and perform a kind of transformation on this kind of region, okay? So we know that the principal value of the square root of z, so z being a substitute for z squared plus z to the minus 2, is going to be continuous on the complex numbers excluding the 0 to minus infinity, okay? And so, mind you, continuous because this is where our jump discontinuity is, especially when we go ahead, okay, from here it jumps this way, from here it jumps that way. That's where we split it up. So, we need to determine where do we hit that inside here, okay? Just breaking down the question bit by bit. So, where do we hit 0? And then, where's the ray from that? The ray negative. So really, we're just asking for when argument of z squared plus z to the minus 2 is equal to pi. Alright? We're just asking for that condition. And what we get is, first of all, z squared plus z to the minus 2 is going to be equal to 0 for the minimum case, in which case z to the 4 is equal to minus 1. This gives us the 4 roots of minus 1 and gives us the set where we're within this bound. Okay? It gets a little... Oh, sorry. My bad. This is just the set of minus pi and 0, I think. Sorry, minus infinity and 0. I'll just double check. Right. Okay. Yeah. That is where fz is, sorry, different question. That is where it is going to be. What is this question doing? Sorry, my bad. We might hold off on this one just because there's a little funky business going on. But the main point for this is that we're dealing with a function where we know that the principal value lies in a certain region, okay? And since that value lies in that region, we're then performing the mapping of z to the z squared plus z to the minus 2, okay? So this thing is what's going in there. And then we're defining whatever regions that is appropriate, okay? Fantastic. All right, so this will be diving us into the integration section, complex integration, and it will be, for the first part, somewhat similar to what you guys were doing in vector calculus yesterday, but regardless, we move forwards. Integrals on curves on complex numbers, we always have an initial point and a final point and a range of a curve, which is defined by a certain parameterization. Fantastic. There's little bits of terminology on closed curves and simple curves, but we won't really need to deal with that. We'll just tell you, okay, is it a circle? Is it from here to here? Doesn't matter how I get from those two places. All right? So let's classify some curves, okay? So a simple curve does not intersect itself, and a closed curve just ends where it started, right? So here we have arcs, polygonal arcs, closed polygonal paths, and simple paths. So simple, we spoke about just before. Polygonal just means a finite set of straight lines, and then a closed polygonal path just means it meets back up with itself. Very similar to what we were talking about before. Yeah. Domain is a nice definition. Has to be open and polygonally path connected. We have parameterizations of lines and circles. We can use a straight line for lines. We go from A to B. Very similar to how we do it in vector methods. We just go this in terms of t is equal to a plus ab times t. And we just say t is an element from 0 to 1. Okay? So that's that. And then parameterizing a circle with a center. We love our polar coordinates, so we just apply that as required. All right, fantastic. Next up, derivatives of curves. So moving into integration, it becomes really important to understand what the derivative of a curve means. Really, all it is let's say here is my path. I go from A to B. Now, when I do an integral, I want to sum together all the parts along this path in whatever manner I'm dealing with it, okay? Whether it's summing them with respect to whatever z value they have, whatever magnitude value they have, whatever, okay? But the derivative becomes important because if I parameterize this circle such that, okay, let's use e to the I, let's just use e to the I theta, e to the it as my parameterization. I go from 0 to pi, okay? Fantastic, that works. I go from B to A, 0 to pi. But what if I go ahead and use I2t, okay? Then it would be from 0 to pi on 2. My time has changed, my integral also needs to change. So the derivative is just telling us, okay, relatively, how big are the steps we're taking per unit time, okay? And that just really breaks it down into a nice sense. Yeah. So easiest way to think of this is if I'm moving quickly, I need to pick up more things per unit time, right? All right, fantastic. Anyways, bit of a vector definition. The derivative can be broken down into real and imaginary components, and it is continuously differentiable if the derivative exists and is continuous on AB. We move forwards. Smoothness is just, okay, is it continuous differentiable? Okay. So we double check. Is this smooth? Well, it's a straight line. Yes. Next up is the curve t cubed plus it cubed also smooth? Well, let's think about it. So we have, is it continuously differentiable? Is it? I don't think it does. Yeah, it is not, because we have to deal with it not being equal to 0. Okay? Because if it is equal to 0, it doesn't move. And a lot of our parameterizations are dependent on the fact that we're moving. The biggest thing to think about here is if I go from here to a point here, and I define my, let's say, dx on dt is a function of x. If the function is equal to 0, then I stay at that point indefinitely, right? And so we have to impose this really, I would say, goofy condition of the fact that you are not allowed to sit still, okay? And this occurs on the curve when we're at 0. All right. Fantastic. We'll move on to curve length. Length is just the integral of the curve in terms of magnitude. So we can break it up into all of its small pieces and then add those together to get its length. Okay? Second integral with 1. Yeah, here's a little example. Let's try and find the length of this curve. We go ahead and we integrate it. We integrate the magnitude. We note that the magnitude of I e to the it, e and I, they both have a magnitude of 1, so we break it down, we just left with r, and it multiplies out. Fantastic. Next up, contours. Contour is a oriented range of smooth curve. Okay, so what do I mean by this? We say this parameterization maps to some set, which I'll call delta omega, just to say some kind of boundary. And this guy right here is the contour. Okay, so it's just whatever space I'm looking at. So in other words, just the range. Generally, we like to take them anti-clockwise, but some questions might go ahead and impose it clockwise. But it's really just important to think about which way we're counting. Alright, so complex integration. We note that as integration is a linear kind of operation, we can break it down into real and imaginary components, and those should be independent. That's the word. And so this actually lends itself to a very useful property where we can actually say that, okay, if I'm taking the real component of an integral, I can take the integral of the real component. And likewise for the imaginary, since the real component won't interact with the imaginary. Alright, moving forwards from that, couple theorems. We got linearity, we've got reparameterization, we got by parts, and we've got a magnitude theorem. Okay, so fundamentally, this is just saying that in the worst case, there are parts that will work against itself. Okay, and therefore, in the best case, they will all work together. Okay, fantastic. Here we have an example. We're going to evaluate the integral from 0 to 2 pi of e to the t cos t dt. And so, let's just crack on with it. So, first things first, here we have a little bit of a tricky integral. Okay, we could go ahead and do by parts a couple of times and then deal with it, but it's not nice. What we can do is go ahead and express cos t as the real component of e to the it, as we do right here. Right? And since we're taking integral of a real component, it can be put backwards into the real component of the integral, as we do over here. And since that really just factors out into the exponent, it becomes very manageable. And so we continue forwards until we achieve the integral is equal to e to the 2 pi minus 1, all divided by 2. Yeah, that's that. Let's keep on moving. So, complex line integration, similar to before. Now we have a kind of field that we're integrating over, very similar to vector calculus. Usually that was 1 when we were determining lengths. Now it's just the function where we're talking about. Okay? So, just recall, we got more linearity things, we got the reversal of a curve, and we have the breakdown of a curve. So this is just splitting it up into multiple pieces. So if I have a curve looking like this, I can do this part and then that part. That's all. So once again, we're going to go ahead, look at an example. So let us evaluate the integral of z squared on the unit circle. Now, it doesn't mention which direction we should be orienting this, whether we orient it clockwise or anti-clockwise, but it actually doesn't end up mattering. So, working through this, we obtain, let's just, for some reason, assume that we're going to orient anti-clockwise, because that is a lovely intuition. Determine the derivative, push it into the equation so that we just have the integral as such, and then integrate it. 0 to 2 pi, that's rather funny. It equals 0 because it cancels itself out. Alright, so that's that. Gives me 0. We'll be looking into that a little later, but now we have a more interesting integral. Okay? Now we have an actual contour for it that is not a straight line, it is a bit of a curve, and let's do it. So, integral over this, first things first, define the derivative. So, the derivative with respect to time is going to be equal to 1 plus 2it, and we're going from 0 to 1. Okay? We plug this in. There should be an integral in here. My bad. And really, just plug it into the z conjugate. It works itself out. We end up with a couple components, and when we plug in the bounds, it just works itself out. Alright? Fantastic. Next up, a new question. We're looking at conjugate of z plus magnitude of z squared. And it's from 1 minus I to 1 plus I straight line. So, how are we going to call this? We're going to go ahead and say, okay, phi t is going to equal to 1 plus, actually, there are a couple ways we could do this. We could go it, t being from minus 1 to 1, or we could go it minus I, and then t be from 0 to 2. It doesn't really matter, it's just different ways we can think of it. Okay? And so in this instance, we go ahead and we use the 1 plus it, making sure that the bounds are appropriate, so we're measuring where we're measuring, and we just move forwards. It is very similar to the previous question, just make sure that you don't get your eyes and stuff mixed up all out of the place. Alright, so this is a bit of a question batch, so we'll just go on to a bit more theory. So reparametrization, we mentioned it before. It is actually the reason why we need phi dash t to be following whatever conditions, and really, if it's the same curve, it should have the same integral value, right? So since we're dealing with the same curve, we understand that we can perform a reparametrization, and the value will be the same, okay? Given that the range of my function is still the same, all right? And we're still evaluating with the same metric f, all right? Fantastic. Next up, we got the ML lemma and the estimation. Well, ML lemma is the estimation lemma. It provides a sufficient upper bound as to a lot of our integrals, and it's purely about length and maximum values. So all we're really saying is the maximum value attained on f within my domain multiplied by the length of my integral is the maximum value it could ever attain. And that's really all it is. We can apply this for a lot of convergence cases, okay? And so this will become more useful in a bit, but here we have the little example. Let's go ahead and show that the magnitude of the integral on 1 over z to the 4 plus 1 as a circle, as a semicircle from 0 to pi with radius r, as r goes to infinity, the integral goes to 0. So, how do we do this? Well, z to the 4 plus 1, we use our circle inequality to upper bound that by minimizing the denominator. And then ML lemma, we go ahead and say that, okay, well, given this instance, I have determined the maximum value. Since we're on a semicircle, it's going to be the same maximum value every time. And that maximum value is given by r to the 4 minus 1, the reciprocal of it, okay? Multiplied by the length, pi r, lovely stuff. We get here, we know that it converges to 0 as r goes to infinity, just because the order is much higher on the denominator. Fantastic. One more definition. Contour integrals It's really just defining, with respect to z, how we do these integrals, and it doesn't really matter dependent on the parameterization. Okay? It doesn't matter whatever parameterization we use. Now for some interesting stuff. We have the Cauchy-Riemann theorem, which is just saying that if we are on a simply connected domain, so that is the entire interior of our domain is going to be differentiable. Okay, so that's, let's say this is my omega, and the interior is such that f of omega, f is an element of my holomorphic functions on omega. So that's just saying they're complex differentiable everywhere inside of them. And it just tells me that, oh, it's curl-free, as we saw earlier in vector calculus. And so we got a 0 here. Fantastic. Yeah. We can try applying this immediately. Here's an example. If we use the unit circle, we note that the zeros on the denominator are not touched. They're not included within the circle that we are integrating inside of. And therefore, the interior is entirely complex differentiable because we have the composition of just complex functions, elementary functions. So we get 0 as per the Cauchy-Riemann theorem. Now, an interesting consequence of this is the fact that two contours with the same initial and final points are equal. So this actually works itself out into being, okay, here's two different contours between two same points. If I orient myself going around a circle in this, then what I have is 0 in my integral, right? Because I've just gone around in a loop. And as per Cauchy-Riemann theorem, that must be 0. Since it is 0, it tells me that, okay, this integral up this way is going to be cancelled out in its entirety by the integral down that way. And therefore, when compared to going up, it must be the same. Alright? So it's a little comparison there. But similarly, this actually goes ahead and defines primitives, because now it doesn't matter how I get between point A and point B. Because if there's an integral between the two, there is a specific value of that integral now, okay? Which we call the potential, but rather the primitive. Alright, so we can use this right now. This function is going to be differentiable on what values? So let's think about this. Let phi be any contour from I to minus I, which lies entirely in the set of the reals being less than or equal to 0. So less than or equal to 0, well, it goes ahead and doesn't touch the pole, right? So it's always going to be differentiable, it's always going to work, and therefore we just need to use the derivative. So a couple ways we could do this. We could go ahead and actually determine the integral between the two, but that is a little boring. So instead, we'll just think about, okay, what is the antiderivative to this function? And then how can I do that from I to minus I? So from here to here. And so antiderivative of z minus 1 is just going to be log of z minus 1, and I'm going to evaluate that between I and minus I. Okay? Fantastic. So we understood there is a log value, log function, on which we can take this function for a primitive and therefore determine the value. Okay, so we get log of z being substituted in. So I think I make a little So we have log of minus I minus 1 mind you, this is going to be log 0. It doesn't really matter. But anyways, I minus 1, and we just work them through. Okay, we can determine the values independently to find that, okay, magnitudes cancel, but the arguments are going to add together. Alright, and we get pi I onto I pi onto. Fantastic. Alright, so that's just a little interesting application where we've bundled together a couple things from previously. Now we have Cauchy's integral formula. Okay? Integral formula is pretty similar. However, now we are including the pole in the middle. Okay? So that is such that if I go ahead, orient myself around a circle, and there's some point inside here that is on my denominator, so let's choose z minus w, the integral just works itself out to be 2 pi I times fw. Okay? And so we can actually use this for a couple really quick results. Okay? It's a very quick and easy method. So first up, we have e to the z dz divided by z minus 2 z plus 2. The integral is a circle with magnitude 3, centered about the origin. Okay? Since that has a magnitude of 3, it touches both of these. And so we can actually break this down into two different functions using partial fractions, and then evaluate both using the Cauchy integral formula. Okay? Now, there's a little funky thing that we can actually push forwards with this Cauchy integral formula, the Cauchy generalized integral formula, which now takes into account the degree of the pole. Okay? Which just pushes into derivatives. Alright. Here is a certain example of that. We have, let's just try and spot things. We have w equals pi. We have f of z equals z squared. And we have n is equal to 2. Okay? So, since we understand that, okay, circle magnitude 4, yes, that includes pi. We go ahead, push forwards, okay, general integral formula. We end up getting 2 pi I divided by n factorial, which will just be 2, times f differentiated n times. So double derivative of this will just be 2, and then pi on the end, which should give us my bad. The 2 is the value. The w value is the input to the function, but our function is constant now since we've differentiated it twice. So 2's cancel, 2 pi I should be the result. Alright, fantastic. We holding in there? Alright, fantastic. Let's keep on moving. So here is another example. We're going to show that a function f is an entire function such that the magnitude of f of z is less than z to the k for a positive integer k, and therefore f is a polynomial of degree at most k. Okay, let's think about this. Okay. If it is entire, it is going to be a polynomial of degree at most k. So this means we have roots, and those roots occur k times. Okay? We get k roots. When we work on these k roots, we can go ahead and understand that the kth derivative of f is, just a moment, we'll take a peek at this one. All right. So, what are we trying to show? An entire function such that the magnitude of f is going to be less than magnitude of z to the k. Okay. And so, what this implies is the z to the k term isn't going to exist. Okay, or at least when it does exist, there's always something against it. And so, let's think about this. That means we most definitely can't get k plus n, okay, k plus some number as our maximum degree polynomial. So, given these two facts, we're going to show, okay, now we understand where we're going. If your function, the magnitude of your function, fz, is going to be less than z to the k, then this is just telling us, when we refer back to our inequalities, if it is a polynomial function, then it can be broken down into the summation of magnitudes, okay, or the difference between magnitudes, right? The greatest one at greatest values will just be dominated by z to the k, okay, z to whatever power that function is up to, okay? And so the way that we handle that in this application is going to be such that, wait just a second, here we are. We're defining that if it is entire, we can take a derivative at beyond powers of that, and it equals 0. So in other words, we're showing that the maximum power is z to the k. Okay? That's where we're at right now. If z to the k is the max power, then all derivatives like this must equal 0. But we also know that the derivative is also of the form n factorial on 2 pi I integral of this value. The magnitude of z to be just sufficiently large, some r number. Understanding this is pretty much just our circle inequality. We just move forwards with it, and we can actually determine the magnitude of this interior. Okay? And it ends up being r to the k over r minus magnitude of w, all to the power of k plus n plus 1. And so, ML lemma, we're going to go ahead and say, okay, since the interior is maximally this, that's the maximum value it can take, we're going to multiply that by the radius, and so we end up multiplying by 2 pi, okay? 2 pi r. And that gives us this value, all right? Now, given that r is just an arbitrarily large number, and n is just any positive integer, we can let r go towards infinity, and we can just consider any n. So smallest case will be n is 1, for which case we know it no longer works. But we note the biggest important thing here is that as long as r goes to infinity, this goes to 0, okay? This goes to 0. And since we understand that, we've just defined a function by its derivatives, which kind of lands into Taylor series. But the most important part is the fact that we get this fact proven. The fact gets proven by performing the integral with the ML lemma, okay? Which is kind of crazy. So, little bonus theorem, we've got Louisville. Louisville just means that if f is a bounded and entire function on the complex numbers, so yep, then f must be a constant function. So really, this is just saying that if you somehow manage to restrict a function between any bounds and it is differentiable on all complex numbers, it has to be constant. Why? Why do we think this? Well, we'll deal with that when we get there. Okay. We also have Moir's theorem, which is just that if you have a continuous function f on a domain given by omega, for every closed contour, we have that f is analytic on that interior. Okay, so it's kind of the backwards version of us saying that, okay, if it is differentiable on here, then the integral must be 0. It's the backwards of that. Okay. Just about this one, the easiest way to think of this is to say that, okay, if I have a function and it has certain zeros somewhere, okay, just as I define it, then if it has a 0 in all these places, you would expect there to be some manner of growth as it eventually hits some kind of last 0. Okay, that's the kind of gist. But if you understand that a function has to have finite zeros, then this implies that, well, if you have even 1, then it must go unbounded. And otherwise, you have no zeros. And what that implies is you are constant. That's kind of where Louisville expands upon. But we will continue. So let's find all entire functions f of z such that magnitude of f of z is less than or equal to cos of z. So, well, that's kind of crazy. We have an entire function that is bounded by cos of z. Okay? So, how do we take this? What do we think about this? We go ahead and we need to consider the function of the division. Okay? So now we can say that g is a function that is definitely bounded. Okay? So, if we go forwards and define any point g of w as the limit point, then we can say that, okay, over here, g is bounded. Fantastic. As a composition, it is also entire. It must be constant. And therefore, g of z must be a constant, and so f of z must be some constant multiple of cos of z. Okay? It's a funky little way we work around the problem by saying, okay, Louisville says entire, we're halfway there, it needs bounded. How do we get bounded? We need some constant somewhere, we just divide it, and it is a composition of elementary functions. Okay? Alright. Fantastic. So now I think we're jumping into our last component with 40 or so slides to go. We're going to run through series, residues, and their applications. Okay? We're going to power through this. Good luck, you guys. So, first things first, power series, calling back to first year, we have radius of convergence and a center of convergence. Okay? We can kind of just define this center by z0 and then worry about the radius of convergence later. But yeah, radius of convergence is typically given by this formula, but you can also take it as the supremum of, what was it, an to the power of 1 on n all inversed, the entire thing, as your radius of convergence. That's just a little thing as n equals 0 to infinity. You check all this stuff. Anyways, it ends up working out to the same value as this. All right? Moving forwards, we can just apply this immediately. So let's find a center and radius of convergence for this power series. I found the center. It is -3. And the radius of convergence, well, it is going to be equal to 1. Because the ratio test, I perform an on an plus 1, which is just going to be n on n plus 1, as n goes to infinity, not 8, which is just going to be 1, okay? And so we say radius 1, that works. Fantastic. Because if I pick any value less than 1, this power box decays it exponentially, okay? All good? All right. Fantastic. Let's keep on moving. So, find an expression for h as an elementary function. Okay, well, we have a sum of powers. Let's think about this. It kind of like works itself out, but we have an n, we want to get rid of n. There's an n minus 1 over here that we can introduce, and derivative and integration becomes our best friend. So we just call it the derivative of z plus 3 to the power of n inside that summation. Note that the power values change, okay? So that is just something a little bit important to think about, because when n is 0, it's just 1, which is just your original, okay? Moving forwards, we can express an integral. Since we know it's convergent within this area, we can push the sum into a geometric sum, okay? In the factored form, which is this, which we further simplify to be the derivative of -1 on z plus 2. Now we just need to differentiate it back again. So we've integrated and then differentiated. So it's using this tool to work with it in different spaces, okay? Which can be very helpful, especially when you need to deal with n. Whenever you see n, it should be a big hint. So next up, third part of the question, where is h analytic? So that is just where it is differentiable, and it is differentiable inside the ball because it converges inside there. And we're just dealing with this function inside the ball, which we know is differentiable inside the ball. Fantastic. All right. We had that. We have another example, n plus 1. We can think again. N plus 1 here, and over here. I'm likely going to differentiate and use that same line of thought. So, first of all, standard form, there's a 2 in front. Sometimes we might want to deal with that, but in any case, we're going to be taking the derivative, okay? And the derivative just becomes a geometric series, which we can go ahead further simplify and then go ahead and reintegrate, okay? So differentiating, integrating, forwards, backwards, it can occur either way, as long as you go ahead and recalculate whatever constant you're dealing with, okay? Typically, you can determine a constant value by just plugging in a specific z value, which might just give you zeros for the remaining part. So, for example, if I want to find the constant part here, I can go ahead and as I go over here, plug in z as 5/2, which is the center of our radius of convergence. which means all of these powers go to 0. And if we look in our original case, that would leave us with either 0 on both sides, or if there was some n equals 0 term, just the n equals 0 term. Okay? So we use that. Fantastic. Alright. So we defined it. Fantastic. Now we have Taylor series. Taylor series is just the way that we can format any function into this kind of power series. Okay, it is a form of power series, and when we center it at about 0, it is also called a Maclaurin series. Okay, but yeah, we move forwards. Determining Taylor series. Well, we know the Taylor series of E. We mentioned it a lot earlier. We're just going to tack on a power of z plus 2. Okay, so E is just the sum of powers over their factorials. And yeah, push a z into this one, push 2 into this one, and then we are very happy. We do a little bit of refactoring just because we want to group up all of our z's of the same power. And so we want z on the outside, we manipulate it so. Okay? Fantastic. Next up we got a Laurent series. So Laurent series is a little bit goofy, but it is really taking into account the fact that we have different poles in different areas. Okay, fundamentally, it can be like really important to say, okay, let's use a function given by 1 on z plus 1 plus 1 on z plus 3. Okay, now in this case, if I center my Taylor series or power series, whatever, about 0, well, I have to think. I get different Taylor series depending on where I go. Because I know that there is going to be a pole at -1, a pole at -3, and therefore it obeys different rules in different areas. Okay? So, that way, we get to push forwards with this kind of question. We're using the annulus given by magnitude of z minus 1 is going to be greater than 1. Okay, so this is going to be an open circle about 1, so it's about here. And we're gathering everything outside of it, okay? Okay, so that means that we don't include this one. We don't include this one. In other words, we know that that one, when we break it up into partial fractions, is going to converge. We know this one will is about z minus 2. So it will converge depending on where we are, and that one will also converge depending on, diverge depending on where we are. But anyways, we push forwards into Laurent theorem, okay, where we can actually determine the coefficients given by the funky little formula we saw a little earlier, okay? And it's just using the boundary points of that annulus, okay? So let's go ahead and try an example. So, first things first, we want to center it about 1, okay? As we do. So, we will restructure every every partial fraction to have a z minus 1 term, okay? So that means we'll have 1 over 2 outside of 1 on z minus 1, which we get plus 1. Minus 1 plus 1, right? So that's what we will do. And when we do this, now we can start looking at geometric sums and what these represent. Okay? So we go ahead perform that right here. And since we understand that it diverges for just z on its own and z minus 2, we're actually going to divide by z minus 1 and such. So we get this value of the reciprocal of 1 on z minus 1. Okay? This, we now know, does converge. Okay? This does become a convergent series, therefore we can express it as a sum of powers. Right? And so we move forwards and we got that. So we get 1 over 2z 2 times z minus 1 summation, where this is our negative ratio. We keep this just running downwards, and we perform a similar act on this one. Okay? And it actually turns out that we do get a Laurent series where the coefficient is actually cancelling out on the two sides. Okay? It cancels out unless it matches up depending on the power of n in these two instances. But yeah. Alright. Next up, we have Laurent series. So, Laurent series question. Let's go ahead and find Laurent series for f in powers of z minus 2 that converge when z equals I. Well, if z equals I, let's think about this. Let us think about this. I want to center it about I, therefore I have 2 over z powers of z minus 2. So I want z minus 2 plus 2 plus 2i, and then minus 5 over z minus 2 minus 2. Okay, this is what our function is going to look like. I put it into powers of z minus 2, and now I want it within z equals I. Okay, so all this means is I need to think about what is the magnitude of these things in those areas. Okay, well, if I get that the magnitude over here, if I get z minus 2 is going to be what? If it is equal to 2, then there's a chance that it just straight up diverges, which is not good. If for this one the magnitude goes up to root 8, then chance it diverges. So we have to think about this. I want it at z equals I. Okay, when z is I, what do I have? Well, let's think about this. Distance from I is something we need to consider. So, when I plug in I over here, when I plug in I with respect to z minus 2, it gives me root 5. And then when I put it with respect to the two other values, I get root 8. Okay? So main things I need to think about is, first of all, we have the bound of 2 given by this one, and the bound of root 8 given by this one. Now I think about, in relation to these two values, where does I sit? I sits at root 5, which is squat in the middle. Okay? And since it is in the middle, one of these will remain as such, one of them I will perform a reciprocal on. Okay? And so we go forwards. We understand that since the magnitude is going to be greater than 2, since it is greater than 2, then this one, this one will converge as is. We just need to factor it out so we can form the geometric sum, and this one will diverge as is. So we need to break it down into the reciprocal. Okay? Fantastic. Moving forwards from there, we once again have positive z values on this side and pushed negative z values on this side. Negative being the exponent that we're using on them. Okay? And so this actually gives us two different definitions on the coefficient depending on the k value. Okay? Fantastic. Just understand, if there was any overlap, we would make sure to put that together. And in this case, there is no overlap, primarily because we're dealing with k plus 1 on the denominator. Alright, so we have another question. Let's think about this. So suppose that this is our function, find the Laurent series for f in powers of z minus 2 that converges when z equals 0. Okay, let's think about this. Powers of z minus 2. First things first, we want to break it down into partial fractions. Okay? When we start dealing with it. But before that, we can think about just how we phrase these two factors. Okay, so z minus 3 is going to turn into z minus 2 minus 1. So here's a distance 1 that we're dealing with for one of our poles. And then our z plus 2i is going to look like z minus 2 plus 2 plus 2i, which will have magnitude 8 as its pole. Okay. When we have z equals 0, well, the difference of 0 to 2 is 2. 2 sits in the middle. Squat in the middle again. And so one of them will converge, one of them diverge. So we need to take reciprocal of one. Fantastic. So once again, we push forwards. We look at the smaller one. Since the magnitude is going to exceed this value, we need to take the reciprocal. Okay, since it exceeds it, we know that there is some manner of divergence that would happen there within this region. Okay, so we deal with that, and since the magnitude is greater on this component, it works out similarly. Okay, so pretty much just the same systematic approach as previously. We perform partial fractions. We recognize the magnitudes of the poles, and we accommodate for that where we are trying to find a convergent series. Okay? So, pushing forwards, we get negative z values, which will typically always have their reciprocal also carried with them, and then our positive z values, which, once again, different values of your constant, your coefficient, depending on your k value. Fantastic. All right, singularities. Fantastic. We love singularities. They make integration so much easier. An isolated singularity is just a point at which it is not differentiable. Okay, and typically this is just because we have a pole there. Okay, we love poles. Now, you can have a removable singularity, and it is typically of the form where you get a 0 over a pole in the same value range. Okay? And so it is actually able to be crossed off if you redefine that point so that you have a new function that is continuous there. Okay? For some non-zero finite number of integers, you say, yep, you say there is a pole at z0 if sorry, my bad. Okay, so these are the three cases. Okay, so either it is a removable singularity, a pole, or an essential singularity. Okay, so the essential singularity is when we describe the Laurent coefficients. Okay, and the Laurent coefficients, you have a 0 point, you go off to negative infinity, you go off to infinity, if there are no values beyond here. Sorry. If there are no integers n less than 0 such that Cn is not equal to 0. It always gets me how they phrase this a little bit. But basically it's saying that all of them this way are going to be 0. That means that it is a removable singularity. Otherwise, if there is some fixed number of them up to a certain point, then it is a pole of that degree. But if it has infinitely many, it is an essential singularity. Okay, that's just how we define them. A few theorems. So if a limit exists, it has a removable singularity. If you multiply it by z minus that value to some power of k, then at k as n, it has a pole of order n. But if that never exists, then it is an essential singularity. That's how we like to define it. Poles of orders, that's just the multiplicity of zeros and poles. Okay? Lovely stuff. Simple is a nice way of 1. Okay? So, moving forwards, we got poles and zeros. We got 2016 question 2, part 4a. Classify the singularities of z e to the z squared plus pi squared on the denominator. All right. So, first things first, pi and minus pi times I, because z squared plus pi squared is on the denominator. These are our poles. Fantastic. So, we move forwards. Let's double check at these points what the limit is. Okay? So, let's look at the numerator. Does the numerator equal to 0 at these points? No, it doesn't. Therefore, it is not going to be removable. Okay? So, we try with power 1. After this attempt, it breaks down and gives us a proper value. So that becomes a simple pole at I pi, and we do the same thing with the limit for minus I pi. Okay? Fantastic. Now, we're going to classify the singularity of this one. So, at z, we check in 0. When we chuck in a 0, what do we get? The numerator is non-zero, therefore it is not removable. We then multiply by z to remove it, determine the limit. It exists, therefore it's a simple pole. At 4, there is a degree of 3, and then at 2, we observe that the numerator is equal to 0 at z equals 2. So we apply L'Hopital's rule to determine the value. Okay, and it turns out we can, therefore it is a removable singularity. Fantastic. Alright, so third order pole at z equals 4, as we mentioned before. Now we have residues. Okay, so a residue is just like, you suppose f is analytic on a, this is meant to be a punctured circle, punctured ball, B, Z0, radius R, Z0 as its center for some R greater than 0, with Laurent coefficients within the ball. Okay? Now, the residue of f at Z0 is given by the coefficient minus 1 in the Laurent series. Okay? And there are a couple of reasons for this, but fundamentally, we love this formula because it has implications to complex analysis and integrals. So, moving forwards, let's go ahead and try and apply it. Alright, so let's just remember the residue of f at z0 is given by 1 over n minus 1 factorial times the limit as z goes to z0 of the derivative of the order n minus 1 of z times z0 times n to the power of n, of f of z. Okay, so this is this z minus z0 to the power of n is just to nearly remove that pole as we're calculating. Okay, as we're calculating the limit. All right. So, residues, let's push forwards. So, here's our example, gz, z minus pi squared over sine squared of z has singularities at z equals k pi. All right, let's calculate the residues at these singularities. Okay, so let's look at first residue. At the first residue, we chuck in z equals pi. Since it is a removable singularity, since it has a 0 of degree 2 and a pole of degree 2 at the same point, it's removable, and so it has a residue of 0. Okay. At z equals 0, there is a simple pole because it has a pole of degree 2 and a 0 of degree 1, and therefore the limit does not exist. And so, simple pole, we go ahead, n is 1, so we go 1 over 0 factorial times the limit as z goes to 0. We multiply by z squared, we multiply by z, so we end up with a z on sine z. So this is our pole section, and then kind of a useless bit of z minus pi all squared. Okay, but when we sub in 0, the limit goes that z over sine z as z goes to 0 is 1, and so we're just left with what's on the right hand side, which will give us pi squared. Okay, so we get a residue of pi squared. Fantastic. All right, similarly we can look at all the other poles. They're poles of order 2, and therefore we would multiply by z minus k pi all squared, which is kind of goofy. So instead, let's just determine the coefficient of z minus k to pi all inverse in the Laurent series. So first we have the Taylor series of sine squared z, just so that we can really put this into our coefficient range rather than dealing with a trigonometric function. We love polynomials. All right, so we do this, we plug it in, and we can see that the coefficient attached must have a rewrite of our function. Okay, so rewriting the function, we obtain this little block of nonsense. By pushing it into partial fractions, by pushing it into its Taylor series, we can expand it into different coefficient values. Okay, and so what we obtain is pi k minus 1 all squared, 2k pi squared k minus 1, which works itself out into pi squared 3k squared minus 4k plus 1. All right, and so the big trick here is just really breaking our sign into its respective Taylor series and then pushing that to get different z values. Okay, fantastic. All right, so let's move forwards. There's Cauchy's residue theorem, which is just saying if we have a contour with poles zk within the contour, we just take the result as being 2 pi I times the sum of those residues. Okay, which is really interesting because it is very, very similar to how you might look at Gaussian integrals. But more so it's an essence of divergence. But anyways, that's just how poles work within complex analysis. So let's push forwards. Let's apply this. So let's go ahead and run through how many more questions we got. We got a couple more questions, and then we're into solving integrals. Solving integrals is just where we bring this back together into real numbers. Okay, so let's try one of these examples. Let's consider the function f defined by z over 2 times z to the 4 minus 5z squared plus 2. Find all the singularities of f and classify these. So let's think about this. We have to factorize the denominator. We get 2 squares, product of 2 squares. Break that down further into these ones. You end up with z being equal to plus minus root 2 and plus minus the reciprocal of root 2. You can see that they're very clearly simple poles just because the numerator only has a 0 at 0. Fantastic. So they're all simple poles. Next up, we can just determine the limits for the residues just by multiplying out those poles, and they work out very nicely. We end up with 1 over 6 within 1 on root 2 and minus 1 on root 2, mind you. This is the ones that are lying within the unit circle, so we don't really need to worry about the ones with a magnitude of root 2. Moving forwards, now by taking an integral over the unit circle, we see that those 2 residues are the only ones we really need to consider, and so 2 pi I times 1 over 3 gives me 2 pi I on root 3. Okay? With the I out the front. Fantastic. All right. Now we're going on to the solving integrals section. So here we have a very interesting function. Okay? Over here, we're going to consider a reparameterization. We're going to consider this as a parameterization of a complex integral. Okay? And so instead, we're going to break e to the I theta. We're going to break we're going to break e to the I theta into z. Okay? So we're kind of pushing our parameterization backwards in this instance. And what it shows us is a number of poles, which we know are going to need residues for. Okay? Given that we're working inside of a unit circle. So that gives us this one and that one, which will be 0 and a half. So moving forwards, we go ahead and we're able to determine the residues and therefore determine the integral. Okay? So it's a really interesting way where we can break our integral down into really fundamental components of, okay, what's inside and then what are the residues. All right, let's spot one more fantastic question. Let's go with this one. So typically what you'll see integrals do is they'll go, okay, from minus infinity to infinity, I want to determine something over here. But in complex analysis, what we'll do is we'll go ahead, draw a semicircle, and let that radius expand to infinity, and say that this highlighted section of the integral goes to 0. And therefore, the complex integral ends up being equated to your real integral. Okay? By using your Cauchy residue theorem. Okay? So, let's just take a glance at this last question before we say goodbye. Let's use complex analysis methods to find the integral from minus infinity to infinity of cos 2x over x squared plus 4x plus 5 dx, and I2, which will be this one. Now, funny thing to note is that these two guys, cos and sine, they work well together. It looks like we can join them together to make a complex integral. Fantastic. So, complex integral, we just sort out the residues. Sorting out the residues gives us a complex limit. Fantastic. And then, just by realizing the denominator, as well as considering the main point of like what this integral is going to mean, we want the real axis taken, okay? As we just mentioned before. And so, we've shown that this integral on this semicircle, as it expands to infinity, or of whatever size, is going to be equal to this residue, okay? And so now what we need to do is show that this external part is equal to 0. So we use the ML lemma and determine the maximum size. Since r has a greater power on the denominator, it converges to 0 as r goes to infinity. Therefore, we can very nicely say that 2 pi I times the residue equals this guy equals pi on e squared of cos 4 minus I sine 4, which implies the integral is equal to that, and therefore we can just break it into real and imaginary components, giving us our answer as required. Okay? Thank you guys very much for listening, and the best of luck with your exams. And yeah, good luck, you guys. You guys did it.